Magic! Away! 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 Away!
Got a little drawing here, what I was talking about earlier, about black holes and elementary particles. Now, for those who don't know what black holes are basically matter that has been condensed so tightly that its density just becomes bigger and bigger. And when its density becomes bigger, its gravitational force pull becomes stronger and stronger. So it reaches a point where even light cannot escape the gravitational pull of a black hole. So the way it works is matter just collapses in on itself. It becomes extremely dense, so dense that light cannot escape from it. And any light that comes close enough gets zoomed in, pulled in. Everything actually gets pulled in. So what happens is there's a boundary that it reaches where if you go past this boundary, it's called the event horizon, you go past this boundary, you just go in basically. So when you hit the event horizon, everything seems black because no light can escape from this side of the boundary, the event horizon. Everything on this side, the light you can still see. So now here, as we mentioned before, elementary particles are the basic building block of matter, everything that we know. It's the lowest size we have been able to go to, the smallest particle we have been able to go to that we can measure that we believe matter is made from. Now there are other theories. One of the ones that I personally like is string theory, where it says matter is just vibrating strings of energy, and the frequency that they vibrate in depends, the size of what the matter is. Now black holes are considered to be the largest single object that we know of in the universe. There is sort of a dispute there. Some people consider galaxies, clusters of galaxies, to be the largest because they act as well as a single gravitational force. They move together. But let's assume black holes are the largest objects in the universe, elementary particles being the smallest. Now, the three properties of elementary particles are, as we wrote down here, spin, force, charge, and mass. So, elementary particles have a certain spin, they have a certain charge, and they have a certain mass because they're extremely small, right? Black holes as well, they have the three properties that we can measure are spin, charge, and mass. And the way we tell the difference between these is, they could have the same spin, they could have the same charge, but obviously one is larger than the other, so their masses decide, if one is a black hole and if the other one is an elementary particle. There's a snag to this. The snag is, in general relativity, there is no size limit to a black hole. So the way it works is black holes could be, actually there is a size limit to how large a black hole could be, and I believe that's the mass of the universe. Condense it all into one thing, and that's a black hole, right? That's the singularity. I guess you could call it singularity. But there is no bottom limit, lower limit to how small a black hole could be. So if you take a black hole and shrink it down to the size of an elementary particle, all of a sudden when you're looking at the smallest part of the universe, which is basically quantum mechanics, where the laws of quantum mechanics apply. Over here the laws of general relativity apply. Over here the laws of general relativity collapse, right? So take a black hole and shrink it down to the size of an elementary particle, you wouldn't be able to tell the difference between the two, because they could have the same spin, they could have the same force charge, and now, they could have the same mass. So in these two extremes, the equal sign changes depending on the size, but the object, the material stays the same. What we're talking about stays the same. So basically, if we were laying down the equal sign, this is what it would look like between small black holes and large black holes. The two extremes of matter, the physical universe that we're talking about when we're talking about large black holes, small black holes, and elementary particles, the laws of quantum mechanics apply on this side, general relativity applies over here, but we haven't been able to, put the two together, really. And that's where units comes in and the equal sign comes in. What is it exactly that we are talking about when we're talking about an object? It all depends on what the properties are of that object that we are talking about or that we're going to compare. Now, in mathematics, we always say, something is equal to something else. But as soon as you introduce Robert Anton Wilson's maybe logic, and that philosophy is just basically there are no absolutes in the world, or there are very few absolutes in the world. What he was trying to do was remove the word is from his vocabulary and basically say things like maybe, could be, right? Or in my perspective, this is the way things look. And that's where elementary particles and black holes, sort of the idea comes together where between large black holes and small black holes, the only difference between them is their masses. And between a small black hole and an elementary particle, we don't know what the difference is because we can't measure the difference, so we don't know what we're looking at. So an elementary particle could be equal to a black hole, or a black hole may be equal to an elementary, and maybe black holes happen to be the building block of everything that we know, right? So right now, in science and physics and our understanding of the universe, we're at a sort of a crossroads where, we know certain things don't make sense. I guess that's the way it's been throughout history, but right now it just seems to be, coming to heads where a lot of things don't make sense, or we're trying to make sense of them, and a lot of things are falling into place, right? So that's where we want to go with this, and mathematics is the language we've come up with to talk about all of this. I hope this made sense. I hope I didn't blab on too much. I just wanted this to be a sort of a teaser for zero and infinity, and just get the idea across again to start looking at the equal sign in a different light, where when they start saying something is equal to something else, always keep in mind that there are properties associated with these things that we're talking about, right? There are assumptions here that we're only talking about certain properties of these things that we're comparing. And if based on these specific properties, then yes, this is equal to this. If we're talking about it in general, this may be equal to something over here or multiple things over here. And that is the importance of the equal sign in units, and that is going to hopefully directly kick us into zero and infinity, and we'll explore some of this stuff a lot further later on, and see where we end up. And thank you to Robert Anton Wilson. God bless you because of your maybe logic. We'll talk later. Bye-bye.
We can't make meaningful statements about one reality. All we can do is talk about comparative realities as perceived by different instruments, which includes the instrument that reads all the instruments, which is the human nervous system. Not the brain, the whole nervous system.